so let's start from the beginning of what was I saying, what I was saying last time. So, after looking at the aggregative clustering procedure, where you take singletons and you join them together, you merge them together, now I was introducing a different way of clustering objects, which is suitable for objects that have a vector representation. So now we are assuming that the objects that we want to collect together in groups have an internal representation. Let's say, I don't remember what letters I used last time, but let's say that our set of objects, for example, probably I used the D, right? So the elements were small d. Okay, so let's keep this. So we have a set D, which is made up of objects with n coordinates. And let's write D. Suppose that we have, of course, a finite number of items in our set. We want the M, so M is the size, is the number of objects that we want to cluster. And we want to group these elements together into k different clusters. So the numbers that we have to keep in mind are, okay, the dimensionality of the space, of course, the number of elements, and the number of clusters. Clearly, k should be much smaller than m. So we may have millions, billions of elements, but we want to merge them into few clusters, 2, 10, 50, depending, of course, on what we are doing. Okay, so this is the setting. Now, the idea here is that every cluster is represented by its own coordinates. Of course, D1, Dm are vectors. Okay, every, let's say, clusters are represented by vectors mu1 up to mu m. Okay. And the idea is that if we have some groups of items like this, we want our cluster to be represented by vectors that are central to each of the groups. Okay, so also our clusters are placed in the same space as the elements.
Sorry. Shouldn't it be mu k?
Mu k, sorry, you're right. Yes, we have k clusters, so in this case, in fact, k is equal to 3. Of course, k equal to m would be the extremal case in which every element is its own cluster, but it's of no interest for us. Okay, so we need a way. So if every cluster is represented by its own vector, how do we decide what cluster every element belongs to? So, for example, so what cluster for element di? How do I decide where di belongs? So the idea is that every element of our set belongs to the cluster whose representative element is closer, is nearer. So the cluster of element I, let's say Ci, so C is for cluster, okay, is so is the index, is the cluster index that minimizes the distance from the representative. So, in some sense, we can say that element di is represented by vector mu Ci. Okay, when we cluster according to this method, we somehow we want to replace every element with its representative. Every element will be represented by the closest representative. Okay, so let us just keep in mind this definition. And let's see how we can place our representatives in the best possible way. So the idea is that at the beginning we don't know where the representative should be placed. So we can start with some guess. The idea is that, for example, we can, well, we start by guessing at the number of clusters. If we are lucky, this number will work, otherwise not. We shall see what can be done in that case. So the first thing that we can do is simply decide arbitrarily the cluster of each of these elements. It's one possibility. So, okay. Let's start here. So the idea is that let's say that we like this. For every element, we choose Ci in 1K in a random way. Okay, let's start by saying that arbitrarily this element belongs to cluster 1, this to cluster 3, this to cluster 2, and so on. Now, of course, this cluster attribution will be, of course, suboptimal. Now, once we have a cluster attribution, which will be refined in the next steps, of course. The second point is, okay, we need to decide where the representatives of each cluster will be placed. But we know that every cluster representative should be the centroid, the arithmetic mean of the positions of all the elements in the cluster. We have seen it last time. So, for all clusters J from 1 to K, we determine its position, mu J, as, okay, we need to take the average position of all elements in cluster J. So we have to sum all elements in cluster J. Let's say we want to sum all elements I such that Ci is equal to J. Okay, all elements whose cluster has been set to J. And of course, this will be divided by the number of all elements in this sum. So the number of all i's such that Ci is equal to J. Okay, of course here are, you see many indices of letters, but the idea should be trivial, okay? Just take all documents, all elements that belong to cluster J and take the average position. Now that we have an average position of each, well, what will happen in this case, for example? Of course, if magically all of these elements were selected to be in cluster 1, all these elements in cluster 2, and all these elements in cluster 3, then of course mu1, mu2, and mu3 would be in a good position. In general, since we know, at the beginning we know nothing about the nice clustering of these points. So every point has been clustered at random. So we can expect that elements of all clusters, so the attribution of clusters has similar numbers of elements in all these three parts. So actual mu1, mu2, and mu3 will be probably here in the center because they will be the average of points in here, and points in here. So they will be somewhere here in the center. Now, what we can do now is given the position of our cluster representatives, we can try to improve this cluster assignment. So we can simply recompute the cluster assignment of all elements in our set. But of course, in this case, rather than doing it randomly, we can use the position of this cluster. So, as said before, we choose the index of the closest representative in the current cluster set. Okay, what's going to happen here? What I claim now is that if we repeat these two steps again and again, the cluster representatives will migrate to their each to one of these clusters. Of course, this is an ideal situation in which we have precisely 3 clusters and we chose 3 representatives for them. So what is the idea? Why should this happen? Let me keep this going. You see, this formula is actually a formula that somehow partitions the Rn space into domains that are that can be identified as the sets that belong to each of the representatives. I mean, if I ask you, let's start from 2 points. So consider the case k equal 2, and suppose that we have 2 vectors, mu1 and mu2. And I ask you, what is the set of points that are closer to mu1 with respect to mu2? And of course, on the converse, which is the set of points in this plane that are closer to mu2 rather than mu1? And the answer is, okay, you bisect the space right like this. All points that are on this side of the line are closer to mu1. All points on this side of the line are closer to mu2. Is that clear? Okay, now, if you add the third point, so let's move to k equal to 3. You add a third point, let's say here. Well, everything becomes a little more complex. This line still represents the points that are closer to mu1 or mu2. We can make the same by deciding which points are closer to mu3 or mu2, and of course the separation is this line here. Okay, if mu1 did not exist, the set of points closer to mu2 would be below this line, the set of points closer to mu3 would be above this line. Actually, the line should be perpendicular to the segment that joins the 2 points. So let's say it should go a little higher like this. We can do the same for the set of points that are closer to mu1 with respect to mu3, and we get another line. Of course, the three lines should not necessarily cross at the same point. Let me do it like this, okay? No. Okay. Now, we can just proceed. Okay, now, actually, what we want to do is divide the space into three domains, which are the set of points that are closer to mu1, the set of points that are closer to mu3, the set of points that are closer to mu2. So, actually, some of these lines are of no interest to us. Let me see what remains actually. This and oh. And sorry, I missed something. Oh. Sorry, I need a more asymmetric disposition. So let's say that mu1 and mu2 are here, and mu3 maybe is here. So it's easier to see that the separation is like I'm not very good at drawing. Okay, so oh, right, sorry. In this case, of course, differently from what I was saying, of course the three bisections need to meet together, okay? Because they are the set of normals to the three sides of the triangle. So in this case, they will meet in a central point. So it's easy to see what we should take. So if mu1, mu2, and mu3 are like this, first like this. So actually the three domains are this, this, and this. Okay. So the idea is that every time we have, if we have 3 points, we are actually dividing our space into 3 parts, and each part is the set of points that are closer to one of the representatives with respect to the other. So, if once we place the representatives like this, so once we have the position of the three representatives, then the data points, the original items, are attributed to every cluster depending on their position on this diagram. All points that fall in this domain are assigned to mu1 and so on. If we have more than 3 elements, for example, the 4th element here, then things become a little more complex. In this case, we have a separation here, and probably here like this, and so on. Every time we add a point, this diagram becomes more and more separated. But you see, every pair of domains are separated by a straight line, which is the line crossing the middle of the segment between the 2 points. This kind of diagrams that associate every point with its own domain in this sense are called Voronoi diagrams. Okay, it means that, well, in this case, probably in this case, at the second iteration, everything will be okay, because if the 3 points were originally set like this, their Voronoi diagram would be something like this. So actually, at this step, you see, all of these points will be attributed to this representative, all these points to this representative, and so on. So actually, this representative at the second step would be moved as the centroid of this group of points. So it will fall here, this centroid will fall here, and this will fall here. Okay, so in the case that I have drawn, actually after one iteration, everything will fall at the right place. Of course, many bad things can happen. So let's still suppose that the 3 clusters are very different. Suppose that, who knows that, after the first random attribution of 3 points appear like this. So that when they share domains, they actually cut the space in this way. In this case, what's going to happen? For example, you see, in this case, let's give them some names. Okay, so this is mu1, mu2, and mu3. Well, in this case, you see, for example, mu3 will be only points here are assigned to mu3. So mu3 will move here. Mu2 has some points here and some here, so it will move maybe here in the middle. one of the other side, depending on the number of points that are assigned to it. And also mu1, which has points both here and here, will move somewhere in the center. But once we have made this move, what happens at the next step? So let me redraw the diagram. So we have the 3 sets, and at the second step we have mu3 here in the middle, mu2 here, and mu1 here. So their Voronoi diagram now is something like this. This means that at the next step, mu3 will remain here. Maybe it's going to move slightly because some more points belong to its cluster. Before, some points belong to mu2. In this case, now, all points in this zone belong to mu3, so it will slightly move. mu2, which was initially here because it was attracted by some points here and some here, now is only attracted to points here because all the points in this cluster have been conquered by mu3. So mu2 is going to move here. mu1 is still attracted on 2 sides. Currently, this side belongs completely to cluster 1. This side is only partly belong to cluster 1, while some belong to cluster 2. So we can expect mu1 to move in this direction. At the next step, let's redraw it. We have mu3 solidly in this cluster, mu2 solidly in this cluster, mu1 around here, and now the Voronoi diagram will actually force mu1 to move here. mu2 will adjust its position here. mu3 won't move with respect to before because no new points are added and no points are removed. So the idea is that if the system is well clustered, so there are k natural clusters, and we choose k centers, k representatives, then these k representatives will move each to a different cluster, because the idea is that the first representative that moves within a cluster catches the cluster and pulls and throws away all the other representatives, because the other representatives won't be attracted to this cluster anymore. Okay? Once mu3 has been here, step 2, all this cluster belongs to mu3, and so the cluster was not of any interest for the other representatives, which were so therefore free to move elsewhere. Of course, this is fine as long as we have a well-clustered set, initial set, and we chose the right number of representatives.
So what will happen if we have no proper cluster?
In fact, let's see the other case before. So what happens if we choose the wrong number here? Of course, your question is perfectly legitimate. But, okay, the best we can say is that, okay, if the objects are not well clustered, well, so we cannot expect, of course, to find a clustering if no clustering is present. Anyway, maybe tomorrow we will see some examples at the computer. The computer is much better at drawing things than I am, so it should be better to wait for tomorrow for that answer. Well, but so now let's say suppose that we have 3 clusters, but we choose k equal to 2. What's going to happen? Now, if we choose k equal to 2, then actually, okay, suppose that the initial positions of the 2 class representatives, mu1 and mu2, were these. What actually happens is that in this case, the Voronoi diagram will be just a bisection of the space. So everything that is on one side will attract mu1, and everything that is on the other side will attract mu2. Meaning, in this case, for example, it means that at the second step, mu1 will migrate here, while mu2 will be the average position of this group of clusters, and this will migrate maybe here in the middle. And actually we are done, because in the next step, of course, this bisection will be slightly different. Maybe it will move like this. But once one of the clusters has been caught by mu1, the rest of the clusters will probably belong to mu2. So we have one properly assigned representative, and one representative that has to cope with more than one cluster. And the situation is going to stabilize this way. Okay? Of course, if there are more than 3 clusters, and we have k equal to 2, so again we have one cluster here, one here, one here, and one here maybe. What we can expect after a few iterations is that the 2 representatives will move to the centers of the different clusters with a bisection in the middle. Of course, much depends on the relative size of these clusters, but this also depends on the initial position of the clusters, of the cluster representative. So, if mu1 is here and mu2 for some reason was particularly close to this cluster, then the Voronoi diagram would attract mu2 to this cluster and mu1 to the center of the 3 remaining clusters. So much will depend on the relative size of the clusters, on the initial random attribution of objects to clusters, and so on. Of course, this happens if k, so the number of representatives that we choose, is low. What happens if we choose too many clusters? So, for example, we are in the usual situation with 3 clusters and we choose k equal to 4. But in this case, what you can expect is that well, much depends on some well, many things can happen actually. One thing is this. Well, actually, some of these, let's see, here, okay. What happens if, let's see, some of the J's are never the closest one to any document, for example. In this case, the algorithm is undefined. For example, I mean, so initially, the 4 representatives will be somewhere in the center because all the clusters will have elements of, so elements of all clusters will be everywhere. So the Voronoi diagram will be something like this maybe. Okay, here we are lucky because every element has at least one closer element. Now, what happens next? This will move here, this will move here, this will move here, this will be the average of these elements, it will move here. At this point, we have one element here, one representative here, one representative here, one representative here, and one here. And of course, now okay, the Voronoi diagram is something like this, probably. So, 3 of the cluster representatives are actually close to some point. The 4th element isn't close to anything. What should we do in this case? In this case, actually, the algorithm is undefined. Where is it undefined? Actually, it's undefined here. Because suppose that this is, okay, move 1, move 2, move 3, and move 4. Actually, when we try to compute the new position for move 4, here this set is empty. So we are not adding anything, and this is 0 divided by 0. We don't know where to place this point. What can we do in this case? Well, we can either discard that point, but it can be dangerous. Because maybe there are 4 clusters, but simply for in the initial step this has been left temporarily out. Or we can reinitialize this to some other position just to well, shake things up a little. So, the idea is that in this case we should probably put move 4 again in play by moving it somewhere else, maybe generating new random coordinates for it, or maybe by choosing some points in the set and arbitrarily deciding that they belong to move 4, even if move 4 has no closer objects. We can also have another case. Instead of moving in an empty part, what can happen if we are in a situation where, for example, here we can assume that, okay, it's almost, suppose that it's like this. Now, this representative will move here, this representative will move here. These two representatives will share the same cluster. At the next step, the situation will actually become stable, because once the representatives are like this, okay, these two representatives will be stable at their own clusters. These two representatives will keep sharing the same cluster. So actually, okay, but of course, so I mean, even if we choose more representatives than there are natural clusters, we can still fall into a stable situation where all representatives are attributed to some points of the original data set.
But so we saw that the initial choice for the clusters, or the points that we belong to certain cluster depend, I mean, matters the final solution. So it changes actually the final solution.
Yes.
So randomly is not a good choice, I guess.
We have no choice. I mean, we can do lots of things in this case. As usual, when we have an algorithm that needs to evolve, we always have the problem of bootstrapping the algorithm somehow. Actually, doing it randomly is often a good choice. I mean, if we choose the right number of clusters, then probably it will fall gracefully, everything will fall gracefully into place. The problem is only when we choose the wrong number. But we shall come to determining the right number of clusters. Well, actually, another choice that we can do is, rather than bootstrapping randomly, we can use the agglomerative procedure that we seen last time to first set up, and you know that procedure starts with singletons and then merges. Okay, we repeatedly merge until we have exactly k clusters, and then we use those k clusters here to initialize the procedure. Okay, so we don't start from a completely random choice, but we start with an informed procedure, with an informed situation at the beginning.
So what will happen in that case to the efficiency of the
Sorry?
what will happen to the efficiency of the algorithm in this case?
What we have?
To the efficiency of the algorithm in this case.
I'm not sure I understand.
I mean the running time of the algorithm if we are going to include the agglomerative with this one.
You mean the complexity?
Mhm.
Or, no. In fact, one of the problems of the agglomerative procedure is that it's rather expensive. Okay. In fact, the main reason why we would prefer to use this procedure, if possible, is also that you see, the agglomerative procedure is actually if we have m elements, but maybe I can show you. Yes, the idea is that if we have m items, then for the agglomerative procedure, well, we need to find the two closest items. We have at every step an m square, a big O of m square search procedure in order to find the closest one. How many times we need to repeat this in order to have to get to k elements, to k clusters? We need to repeat it m minus k times. So actually, the agglomerative procedure that finds that finds k clusters is the order of m minus k m squared. And if we assume that k is much smaller than m, we are actually dealing with an m cubed procedure. While here we are actually, you see, okay, this averaging procedure is in the order of big O of m. We just take, if we assume that we already know the cluster attribution, of course. Determining the cluster attribution is actually a big O of k times m, because we need to, in principle, we have to compute the distance between each of m elements with each of k elements. Here I'm taking n, so the dimension of the space as a constant. Otherwise here we should have to add also a big n. But let's say it's a constant, so we assume that the distance can be computed in constant time. Okay, so the problem is that, okay, this, so one step of the agglomerative procedure is m squared, one step of this procedure is km, so actually km is much smaller. There is a catch here, of course. Here we know for sure that the procedure will end after m steps at worst, because every time we are reducing. So n cubed is actually the number of steps, the overall number of steps where the procedure is granted to n. Here, well, we still have to discuss a terminating criterion for this. As far as we know, these two steps can be repeated indefinitely. But each of these steps is much less complex. So in fact, as you suggested, right, my suggestion of using this procedure in order to bootstrap this, okay, can be very costly from the point of view of the time complexity. But a lot depends on what kind of clustering we actually want. I think we'll see some examples later. Anyway, right, how do we decide when to stop? You see, in principle, at every step, some representative positions may change, and as a reflection, some cluster attributions may change. Actually, what we can expect, what is reasonable to expect, is that after a finite number of iterations, this attribution won't change anymore. So every representative will reach a stable position, which is what we can see here. Either one representative has reached, conquered its own cluster, or some representatives are sharing the same cluster together, and their mutual position has reached some stable point. What can happen actually is that we may have some oscillation of points from one side to the other. So we can also fall in some locally to some local cycle, where some point will jump indefinitely from one cluster to the other. But of course, these are cases that only happen when 2 points, two representatives share the cluster. So it means that there are some points that are uncertain to which cluster they should be attributed. So it is probably a case where either there is no a neat clustering separation, or we have chosen too many, we have decided to start with too many representatives. So one criterion to decide when to stop is just to look from one step to the other how many cluster attributions are changed. As soon as the number of changed attributions is 0, well, if the attributions remain the same from one step to the other, then everything is going to remain the same. So the algorithm has converged. Otherwise, probably we should take care that if the number of changes is small with respect to the number of elements, and it remains small for a certain number of steps, then probably we have fallen into a cyclic situation and we can stop. So the criterion that is usually put into place is repeat this until well, let's say the number of modified CIs is 0 from one step to the other. Or number is less than some, well, let's say it has remained much smaller than m for some iterations. Okay, now, suppose that we have executed this algorithm and at a certain point we met this stopping criterion and the algorithm terminates. What can we do about, what can we say about the goodness, the fitness of the solution that we have found? So when this algorithm terminates, we have a precise attribution of every element to a cluster and the position of the cluster. Actually, you see, I have written the algorithm this way because we started with the cluster attribution. So first we compute the positions and then we recompute the attributions. But if we put the termination condition down here, then the new attribution might not be the one corresponding to. So these centroids can be out of date because we recomputed the attribution. So if we stopped with no modified CIs, of course, the mu j's will be up to date. But if we stopped for the second reason, okay, we recomputed the attribution, we also need to recompute this. So in general, let's say that the termination condition should be put here. Every time we compute an attribution, and then based on that cluster attribution, we compute the centroids. Anyway, the algorithm will come out with this set of CIs and this set of MUJs. How do we compute? So the idea is that now we can compute an overall measure of how good is the clustering that we come up with. The idea is that we can compute an error, which is the same that we defined last time. Actually, we defined it for one cluster, but it's the same. So, what is the overall error that we have if we decide to replace each item di with its corresponding representative mu ci? Of course, the error is, so I compute the sum of all elements I of the distance between the element di and the corresponding cluster representative, which is mu Ci. And let's take the square distance, of course, we are always in the Euclidean space. Actually, the whole aim of this procedure is to minimize this error. In fact, this is the reason why we place every representative at the center of its own documents, because it minimizes the local error at that cluster. So we get this formula. By the way, this is often called the quantization error. Quantization usually means that we are discretizing something. We are moving from the continuous representation to a discrete representation, which is somehow the case here, because we move from the representation of each element by itself to a representation that groups together many elements. So we are, in a sense, discretizing the set. We are largely reducing its size from M to K. In fact, that error is precisely the overall error that we commit, that we do, if we forget about each document position and we only consider the cluster representative. So we replace every document with its own representative. Let's see how this error works. Well, look at what happens while we, so suppose that we still have the usual set of elements. Suppose that we choose k equal to 1, the smallest number of possible representatives. Of course, for k equal to 1, the procedure will converge immediately. We just have one possible value for the cluster, so every document will belong to the cluster, and the cluster representative will be the center of all elements, the average position of all elements. So, all documents are represented by this representative, and if we compute that error, we will have a fairly large number, because we are adding up all of these distances. The distances between all documents and this average position. So we can also try to plot the error against the chosen value for k, and for k equal to 1, we will have a fairly large error. Let's call it E1. Now let's move to k equal to 2. Now, as we have seen, if k is equal to 2, one of the representatives will get first to sum to one of the clusters, and the other representative will be somehow in the middle of the remaining ones. We are considering a system with 3 natural clusters. Okay. In this case, you see some we are adding these large distances and these small distances. So actually, for k equal to 2, of course the number of the quantization error will be lower, because some of the contributions have reduced because one of the representatives have reached a cluster. Okay. Now, of course, things are still getting better when k equals 3. Because every representative has reached its own cluster, and distances and the contributions to the overall quantization error will be small. So for k equal to 3, we'll have another substantial reduction of this quantization error. Now, for k equal to 4, nothing will substantially change. Of course, you see, if we add a new representative, as we have seen, the worst that can happen is that all clusters will be appropriated by some representative, and one of the clusters will be shared by 2 representatives. So some of the distances are from one representative and some other distances are from the other representative. Of course, the larger the number of representatives that we put, the smaller the error. So every time we increase k, somehow we will reduce the quantization error. But the step from k equals 3 to k equals 4 is negligible with respect to the others. We have significant reductions in the first steps, and then negligible reductions when we move to more clusters. So actually, if the set of items we are dealing with has a natural clustering, then if we repeat the clustering procedure with increasing k, we get to some point where we can say, okay, here we are, let's stop. Because you just need to measure the delta between subsequent quantization errors. You will find one point where the quantization error does not change that much. Of course, this is not always the case. I mean, what we have usually is not the case like that, but maybe some case where we have points everywhere, but with more density on some specific places. In that case, of course, we can expect the the quantization error to decrease, but not that dramatically. In this case, for example, we will always have, for k equal to 3, for example, the representatives will tend to move to the centers of these density distributions, so that we still have a good separation between three domains. But of course, there will always be some large contributions to the quantization error, because we will always have points that are distant from the center of the cluster. In this case, this is one of the cases where we can have oscillating behaviors here that prevent us to stop with the neat stopping criterion. Because in this case, small movements of these centroids will cause the Voronoi diagram to switch some points from one domain to the other and prevent us from stopping that. But anyway, also in this case, we shall see a decrease that is large up to a certain point and small afterwards. Maybe, of course, we will have a slightly less, a gentler curve, well, if not curve, because we have, of course, a discrete number here, but we should find a point where there is no reason to move beyond. Okay, this algorithm, okay, it's called the k-means algorithm. You are actually trying to find k different arithmetic means of your set. And what I have presented here is actually its hard version. What does hard mean? Actually, it refers to the fact that we are associating all elements to a given cluster and proceed from that to move the centroid. So this algorithm has is an iteration, and every iteration has two very distinct phases. In the first, we determine a cluster for every element, and in the second, once the cluster has been determined, we proceed with computing the centroids. Actually, this algorithm can be relaxed in well, lots of different ways, leading to softer versions of the algorithm. One idea is that rather than proceeding by steps like this, well, let's see, and somehow the other extreme. We can do this. start this time from, let's say, for every j, let mu j be a random vector in our space. This is not well defined, okay? We can just say a random vector here and there. Let's say, for example, you can assume that we limit our choice of randomness in the bounding box of all elements, for example. So we're not choosing one vector here, one here, and so on, but we restrict our choice inside the space, or maybe even just a random element in our, oh sorry, this was n, okay. Maybe we initialize every representative to be one different random element of our set. Or the average of random elements in our set. Anyway, let's start with an arbitrary random distribution of our k representatives. Say one is here, and the other is here. Okay. Now, what I want to repeat is a much simpler step now. Rather than computing a hard attribution, so the like before, computing the CIs for every I, we just choose one random element. We see which of the representatives is closer to it, and we pull the representative slightly closer to this element. So, we choose one random index, so we choose one element in our data set. Of course, we need to decide which is the closest representative. So we compute Ci for that particular element. And we modify mu Ci by moving it towards the point di. So let's say no, not move. Let's say theta. So, what I'm proposing here is that every time we take a document, we slightly pull the corresponding, the closest representative towards that document. You see that, for example, okay, eta of course is some parameters that we need to decide at the beginning of the algorithm, and it will be in the range 0, 1. Of course, neither 0 nor 1 are useful to us. In fact, you see, if we choose eta equal to 0, then we are not moving anything and all representatives stay where they are. If we choose eta equal to 1, then we are forgetting about the previous position and we are making the representative jump to the document's position, to the element's position, which we don't want. So, we need, of course, to set up this value for eta. You see that actually the dynamics is not very different from what we have seen in the previous case. I mean that once some elements have started pulling their own representatives to themselves, then this representative will always be considered when using these elements. And so it will never be pulled out by other elements which will find more different representatives for themselves. So also in this case, maybe we can see some practical example tomorrow. Maybe at the computer we can better see how things move. So in this case, you see, the step is much simpler. Take one element and pull the corresponding representative towards that element. So this can be seen as the prototype soft k-means algorithm. In this case, we can have many different variants of the algorithm. For example, okay, we can have many variants when deciding the initial representative position. We can have variants where the eta coefficient is not constant, but it decreases as long as the algorithm proceeds. The idea is that you want large jumps at the beginning and then smaller jumps towards the end where only local adjustments are required. So maybe eta, rather than being constant, is going to be decreased. Another possible choice is a probabilistic one. Okay, rather than always choosing the closest representative to the document, maybe we can choose randomly the representative, but with a probability that is inversely proportional to the distance, so that the closest one is chosen with higher probability. Okay, and this is good if because somehow there are some situations where we want to pull some representatives away from some local minimum. But maybe we can see examples tomorrow. Okay, so at the end, what is the main drawback of this algorithm? It's more difficult to say when to stop. because, okay, the first drawback is this: we have to carefully choose one value for this, and maybe a schedule for decreasing it as long as the algorithm proceeds. The other problem is that the stopping criterion is difficult, because you see, no matter how long you proceed with the algorithm, every representative will still be moved at every step. In this case, well, you can resort to two different stopping criteria. Either you say, okay, I'll allocate this time for the procedure. Let's run it for this time and assume that what comes out is a good clustering. So repeat until time has expired, of course. The second criterion can be linked to the quantization error. Look at the quantization error. It's going to, probably it will follow some, as long as time proceeds, in this case, if you look at the quantization error with respect to the number of steps, you will find something like this. Well, of course, it's not going to zero, but it's probably going to stabilize at further iterations. So you can recompute the quantization error from time to time and decide when there are no more significant decreases in the quantization error. You don't want to compute the quantization error at every step, because you see, the advantage of this is that the basic cycle has a very low complexity. Actually, the only place where we need an internal loop is this, where we are given the document and we want to find the closest representative. So this step, this loop, every iteration of this loop has a complexity of big O of k. We decided the document, and we are looking for all representatives for the closest one. The expensive step is this, and it's big O of k. While, of course, computing the energy, well, a physicist would call this energy. The error is at least a big O of m. We have a sum that is for all m elements. Assuming that this is pre-computed, so we know precisely what representative for every document. Otherwise, it would be more complex. So here we want a basic loop that has a big O of k iteration, and maybe from time to time we accept a big O of m step in order to see what happens to the quantization error as time proceeds. So the two algorithms that we have seen, so the two versions of the k-means algorithm, okay, they are very different from each other, but they are still based on the same idea. Let us represent every cluster with its own representative, and let's move representatives in a convenient position in the cluster so that this error is reduced. we explicitly reduce this error in the hard k-means procedure, where representatives are always put at the centroid, because in that way we explicitly reduce this. Here, the reduction is not immediately visible, but still, since every representative will be actually pulled to a different cluster with a similar mechanism, still we are reducing that error. Of course, we can have many mixtures of the two versions of the k-means algorithm. And let's see. Anyway, let's keep in mind the soft version, because next time we will see other variants, because the soft version can actually be extended to more complex tasks. So not only clustering. Okay, I think that today we are done. Tomorrow, maybe we'll look at some examples of this. Then next Monday we will continue with other clustering and other algorithms for dealing with a complexity reduction on data. Okay. Okay.